Okay, this final webcast on the Projectile Motion Lab talks about the end of part 2. So we have we found a physics equation for the graph of flight time versus the square root of height. There is a relationship there, but we've realized that the graph of flight time versus height was curved, and it looked like the square root function. And so we took the square root of the height in order to make it a linear graph so that we could find the slope and write the equation of motion. Okay, so we have this physics equation now, and the question that we're trying to answer now is there a physical significance to this slope? Okay, and so the activity sheet gives us this equation. This is one of the kinematic equations. It's been slightly revised from what you're used to looking at because it is written in terms of applying to motion in vertical direction. So, for example, instead of displacement being called delta x, we're calling it delta y because, think about when you look at coordinate axes, the x-axis goes left and right, the y-axis goes up and down, okay? So displacement is written in terms of a change in the y-coordinate. And then when we talk about the initial velocity and the acceleration, we have little subscripts there to say that they pertain to the vertical direction, okay? So it's the velocity in the vertical direction, the acceleration in the vertical direction. Okay, so the projectile was launched horizontally. So the initial velocity in the vertical direction is 0 meters per second. Okay, and the acceleration in the vertical direction is acceleration due to gravity. So that's negative 9.8 meters per second squared. And, okay, so we've got those things, and it says let's solve this equation for to find the delta t. This whole first term right up here, VIY times time, that equals 0 because the initial velocity in the y direction is 0. Okay, so I have that the displacement in the vertical direction equals 1/2 the acceleration times time squared. And I'm just going to solve for time, the flight time. Okay, so I'm going to divide both sides by 1/2 times AY, and so I get 2 times delta y, the displacement in the y direction, divided by the acceleration. That equals t squared, and so if I want t, I have to take the square root of that. Okay, and if we plugged in the numbers that we know here, delta t would be the square root of 2 over 9.8 times the square root of delta y. So I want to explore this. What is the square root of 2 divided by 9.8? And so let me get my calculator. So the square root of 2 divided by 9.8 equals 0.452. Wow, look at that. That value is quite similar to our slope in the physics equation up there. We had a slope of 0.453, and this square root of 2 over 9.8 has a value of 0.452. Okay. Let's want to just see the units of that. The dimension of the square root of 2 over ay. Let's see what that is. So, well, 2 doesn't have a dimension, okay? But the acceleration due to gravity has a dimension of meters per second squared. So I'm taking the square root of this fraction, 1 divided by meters over second squared. That's the same thing as taking the square root of second squared over meter, right? 1 divided by something is the inverse of that thing. So this was the inverse of second squared over meter. Gosh, that is seconds over the square root of meter. Oh my goodness. That is the same as the units of our slope up there in the physics equation. Okay, so let's see if we can summarize the results here. Okay, so and let's see, I'm going to make this blue so we can tell that it's the answer. The value of the slope of the flight time versus square root of cannon height graph was 0.453, which is very similar to the value of let's see, the square root of 2 divided by g. Remember, lowercase g, that is the acceleration due to gravity. Which has a value of 0.452. Okay, so I can see that the two values are very similar, 0.453, 0.452. But also, the units of, and let's see here, square root of 2 over g, I'm just going to copy that down here, simplify to be seconds divided by the square root of meters. Which are the same units as the slope of the flight time versus square root of height graph. Therefore, conclude that the slope has a physical meaning, which is the square root of 2 divided by the acceleration due to gravity. This physics equation can be put into a more standard, a more general form for any horizontal projectile by replacing the numerical slope with the meaning of the slope, as shown below. Okay, so I'm just going to rewrite that physics equation that said that the flight time, let's see if I can get over there, the delta t equals the square root of 2 times the height divided by the acceleration due to gravity. Right? Or let me be more clear. So our slope was the square root of 2 divided by g, and then that is multiplied by the square root of height. And so what we get is square root of 2h divided by g. And so I could use that equation to find the flight time for any horizontally fired projectile. If I know their height, I could plug that in here because g would be 9.8, their height would be whatever it is. The square root of 2 times the height divided by g would give me the flight time.